Hello everyone! This is one of those examples where the generalized principle of inclusion and exclusion is very useful, especially when we talk about E of 0 already discussed earlier. This is what will happen if m is equal to 0. We have here to find the number of non-negative integer solutions for x sub 1, x sub 2, and x sub 3 if their sum is 15, but given that our x sub 1 is 5, x sub 2 is 6, and x sub 3 is 7. Now take note that the requirement here is that x sub 1 is less than or equal to 5. So since we have non-negative integer solutions, we can have 0 until 5. But for x sub 2, 0 until 6. And x sub 3 was 0 until 7. So we have a lot of possibilities for this. That's why we intend to use complements here for each of the property. Because if we're going to attack the complement of the property and use this formula, because the formula of general formula for E sub m on the GPIE, okay, GPIE is equal to the omega of m minus m plus 1 taken m, omega of m plus 1, then you have here plus m plus 2 taken m, omega of m plus 2, then you have here minus until you reach plus negative 1 q minus m q combination m, and then omega of q, right? So we have a lot of possibilities if we are going to do this. So, but however, if m is equal to 0, this entails a shorter formula. Our E of 0 is just equal to omega of 0 minus omega of 1 plus omega, plus omega of 2 minus omega of 3, and so on and so forth. Okay, so it would be plus, and then again the last one here is negative 1 raised to q, and then you have here, because all of this would become, this would become 1 once our m, the r in our combination would be 0. So you have omega of q. So this is even easier than that. But how do we attack this so that we can use this implementation? Take note that E of 0 is equivalent to saying that number of elements with not having having none. Let me state it like this: having none of the Q properties. If it's having none of the Q properties, it is easier to look at. Let's attack the complement, because our goal, let me make it clear, our goal is to solve for the x sub 1, x sub 2, and x sub 3 having these properties. Okay? If we're going to talk about its complement, say our p sub 1 is now, let's say another notation, a sub 1 is greater than or equal to 6. Okay? That is the opposite of that. Okay? So because this includes 5, okay, for x sub 1, opposite, this is the complement of your x sub 1 less or equal to 5. What if p sub 2 will be changed to a sub 2 greater than or equal to 7? This is the complement of x sub 2 with less than or equal to 6. And p sub 3 will be the complement, we have a sub 3 less than or equal to 8, the complement of x sub 3 and 7. Once we identify its complement, these are the complements of our goal. This is our goal, okay? Once we take the complement of this, and then we use E of O, which again tells us the result of having none of these properties. The result E of O is actually equal to the result of having these properties here. Can you see the connection? If we're going to look at the complement and solve for E of O, which is easier formula, the result of that, since we have the double negative here, complement and having none, it suffices to say that the result of E of O is the result for the item intended. Okay, so hopefully that's clear. So that we could start now with our first method. Our first is to identify these quantities for our E of O. Take note, our omega of 0 is always equal to the cardinality of our S. And what would be our cardinality of S here? Take note, we are picking here the number of integral solutions actually is given before in our chapter, the previous chapter, R plus n minus 1 taken R. This tells us that the number of integral solutions, where n is actually the number of terms and your r would be your total. Okay, so as mentioned in one of the videos in this playlist, we're able to understand that the number of terms for each of a set, in this case, even for this situation which involves PIE and the GPIE, depends on the type of sets we have. We have situations before where set S is just countable until 1000. We have also situations where we talk about positive divisors, where we look into how do we really count number of positive divisors. In this case, how do we count the number of integral solutions? It is given by this formula presented previously. So for our S, our R is actually 15. Okay, so 15 plus a 3. Okay, 3 would be number of terms minus 1 taken 15. So that's actually 19. 17 rather. 17 combination 15. Okay, which is also equal to 17 combination 2, right? So you can come up with a result of that. Okay, so let us have here 17 combination 15 or 17 combination 2. You have here 136 as your result. 136. Now, that's for our omega of 0, because it's already given that it should be the cardinality of S. How about the of course, it's negative later on, but how about the omega of 1? How do we solve the omega of 1? The omega of 1 talks about the sum of all situations where we have the omega of p sub 1, the omega of p sub 2, plus the omega of p sub 3. Not the original p sub 1, p sub 2, and p sub 3 in our situation using this, but the complements. Again, we are attacking through the complements so we can use e sub 0 to solve for our intended target. Okay, so how many? So for our what would be our w of p omega of p sub 1? So for omega of p sub 1, take note that we are on be greater than 6. So since it's greater than 6, how many r would we remain? That would mean in our r, original r, the total, which is 15. Supposedly our r is 15. But for omega of p sub 1, okay, this is what will happen for omega of p sub 1. Now let me have it separately, so please bear with me. This might need a lot of time. So omega of p sub 1, okay, alone. Okay, before we could move into that, actually, your r is no longer 15. The formula is r plus 1 minus n taken r right. But it will no longer be r 15 because strictly we are greater than or equal to 6. So we have here 0, 1, 2, 3, 4, and 5, not including 6. So there are 6 of them. So in short, we will have here our r is actually 15 minus 6. That's our r alone, plus our n, which is the number of terms, 3 minus 1, still taken between 15 minus 6, or 15 minus 6 automatically here. That is because the possibility for our p sub 1 are all those 0, 1, 2, 3, 4, and 5. 6 terms are subtracted. Okay? So this stands for 9 plus 3 minus 1 combination 9, which is equal to 11 combination 9. That's actually equal to 55. Okay? So for our omega of p sub 2, same thing, but in this case this is 15 minus not 6, but since we have here, this is our criteria, so we have 0, 1, 2, 3, 4, 5, 6, actually 7 of them. So minus 7 plus 3 minus 1, 15 combination 15 minus 7, which is equal to, oh, I don't have much space, so let me be using another space later. That's actually 8 plus 3 minus 1, that's 10 combination 8, which is actually equal to 10 combination 8 is 45. Then for the omega of p sub 3, you will have here 15 minus, again, greater than 8, so you will have 0 until 7, that's 8, plus 3 minus 1, 15 minus 8. So you will have here, actually, that's a 7 plus 3, so 9 combination 7, and 9 combination 7 is actually equal to 36. So in short, our omega of 1 would be the summation of all those omegas having exactly one property. So that's actually 55 plus 45 plus 36. So you have 55 plus 45 plus 136. Okay? 136. Again, 55 plus 45 plus 36. Okay? So that's what we need to subtract from our here. okay, from the omega of 0. But since we still have more pairs, we have omega of the pairs of I mean, with 2 properties and the 3 properties. So let's move to another page. Okay, I'll be adding another page here. So sorry for that. I'm going to have here the omega of 2, meaning we're going to add the omega of p sub 1, p sub 2, plus the omega of p sub 1 and p sub 3, plus the omega, that's omega of p sub 2 and p sub 3. All of them at the same time. So simply attack this one by one if you are not yet comfortable with a lot of steps. So again, we have here r plus n minus 1 taken r for the number of what do you call this one? Earlier we note this as number of integral solutions. Now take note, r is still 15, but our p sub 1 is for a sub 1 greater than or equal to 6. Our p sub 2 is a sub 2 greater than or equal to 7. In p sub 3 is a sub 3 greater than or equal to 8. So how many would be added, or if we're going to consider the minimum, 6 and 7 here at the same time? That's why you will have here 15 minus 6 minus 7, the 6 possibilities for this and 7 possibilities for that, as our r, plus 3 minus 1, still 15 minus 6 minus 7 here. Okay? So we are to remove those because those are the possibilities that we have tried. So that is why you have here 15 minus 6 minus 7 is 2 plus 3. Sorry for that. 2 plus 3 is 5. I'm going to automatically write this one, okay? So you have here 4 combination 2, which will give us a result. Very simple. 4 combination 2 is equal to 12. 6. Okay? Now for the p sub 2, let's start with p sub 1 and p sub 3. So p sub 1 is this, 6 and 8. So 15 minus 6 minus 8 plus 3 minus 1. So combination 15 minus 6 minus 8. Okay? So you'll have here actually just 1 plus 3. So that's actually 3 combination 1, which gives us a result that's very easy as well. We have equal to 3. Okay? And then for the last pair, p sub 2 and p sub 3, so you have 15 minus 7 minus 8 plus 3 minus 1. Okay? So you have 15. Your r would be 15 minus 7 minus 8. This gives us a result. That's 0 plus 3 minus 1. That's 2. So 0. 2 combination 0 is just equal to 1. Right? 2 combination 0 is equal to 1. So all of this for your omega of 2. So you simply add them, 6 plus 3 plus 1, you will get 10. You will get 10. Now, let's have the last one because we have here the combination for 3 properties. That's actually the 3 properties. So your r is still 15. Okay? So, sorry, this is, my bad. Let me write here the first notation. Omega of 3 is again the omega of p sub 1, p sub 2, p sub 3. We only have one combination of all. So that's actually equal to 15 minus 6 minus 7 minus 8. Okay? So all of them plus 3 minus 1. You have here 15 minus 6 minus 7 minus 8. And what is that equivalent to? Take note, this is very negative. That's automatically equal to 0. Okay? That's that's obviously very equal to 0 now. Now, so let's proceed now to our target. Again, don't forget that we're taking the complement. So we can now use E of 0. And again, whatever will be the result of that, even if we are using the complements, because E of 0 talks about none of those complements, it will yield to the answer. So the result for this automatically is the answer. E of 0 is equal to omega of 0 minus omega of 1 plus omega of, omega of 2 minus omega of 3. We end up until omega of 3 because we only have 3 properties, right? So we have your omega of 0 is actually given as earlier 136. 136 minus the total omega of 1. So you have here 136 plus omega of 2. The total for that is 10 minus 0. So we have here the result, which is equal to 10. So what does this imply now? What is this 10? These are the number of elements from 0 to 15 that are possible for our solutions here. A number of elements. Yeah, our E is, I'm going to make some implications here. Our E of 0 is actually equal to 10. What is this? These are the number of integral solutions having none of these properties which are stated in complement form. If 10 are not, do not fall in the criteria that a sub 1 is greater than or equal to 6, a sub 2 is greater than or equal to 7, a sub 3 is greater than or equal to 8, and there are 10 of them having none of this. Basically, 10, using the double negation, complement, and having none, 10 integers having the property, or will satisfy the property of x sub 1 be less than or equal to 5, x sub 2 be less than or equal to 6, and x sub 3 be less than or equal to 7 to satisfy this equality. That is why in our GPIE, we tend to use this to attack the complements for some situations that are not straightforward to be answered. So you can see in this situation, this is very long, and we use this idea, hopefully this is very clear, so that we can work on it on some similar situations as well. Thank you very much for watching.